Good morning. Happy Thursday. Good morning, guys. Ready to learn some more probability? I know you are. Not right now. Okay. So we are learning about compound probability today. Compound probability, if you remember compound shapes from our last unit, it's just sticking two shapes together and making a different whole shape. So compound probability is essentially considering two different, at least, sometimes more than one event in our probability. So that can happen two ways. It can happen with and it can happen with or. So you remember our Venn diagram work that we did last time. It wasn't yesterday, Tuesday. We were talking about what it means in math, an and an or. So sometimes probabilities will just directly say what's the probability of this happening and this happening. And sometimes it won't actually say those words, but it will explain what it means and in other words. And so you kind of have to watch for what kind of probability they're asking for. Most of the time, they will say either and or. Um, so the first one we're going to talk about is and, because that one's easier. So and probabilities, first of all, the reason we talked about independence last time is because independence is super important with compound probability. If you're considering more than one event, and you have to know whether or not they're independent, because the math changes one way or the other. You will only encounter independent event. But in the world, you can't do the same math for two independent events as two dependent events. So the events have to be independent. Sometimes they will say that, sometimes they will just assume that you know that because it's like two dice rolls or whatever. So that's important. Two things have to be independent. And then once you know that they're independent, the probability calculation for event A and event B is just the probability of A happening multiplied by the probability of B happening. So you just multiply their two probabilities together and you'll get the total probability for both of them happening. So remember, and in math means that both are happening, absolutely both. Not one or the other, but both at the same time. So in that situation, you multiply the two probabilities. So we're going to do an example. A group of friends, this is this first one. A group of friends is playing spin the bottle. The group spins the bottle twice, and the two chosen candidates have to stare deeply into each other's eyes for a whole minute. Assume that the probability is uniform for each of the 6 players. If one player gets chosen twice, they get to take home the extra cookies. Okay. So the idea is that this is random, right? The bottle is choosing somebody at random from these 6 friends. And first we're going to figure out what the sample size is. Sample space, I mean, the size of the sample space. The sample space meaning what is the total number of probability, like what is the total number of outcomes that could happen, right? So the first time, we're going to use the fundamental counting principle. The first time the bottle chooses, there's 6 options. So there's 6 options for that first one, and then the second time the bottle chooses, there's also 6 options. So our fundamental counting principle will tell us that the total number of outcomes, possible outcomes, is 36. 6 options from the first spin, 6 options from the second spin. And we'll just write total possible outcomes. Yes, There you go. Okay, so number 2, Katie is hoping she and Alice both get picked. What is the probability of that happening? So Katie is one person out of 6. So the probability, let's write this. I'm going to just use our probability notation. The probability of Katie and Alice, is that who the other one was? Alice? Both getting picked is going to be equal to the probability of Katie getting picked and multiplied by the probability of Alice getting picked. So we're going to do this. The probability of Katie, she is one person out of 6 total people can be chosen. Yeah? Then the probability of Alice is going to be the same because she's another person out of those 6 people. So the probability of Katie and Alice getting chosen is going to be 1/6 times 1/6 because we're just multiplying the probability of Katie times the probability of Alice. So that's going to be 1 out of 36. 1 out of the 36 possible outcomes is going to be Katie and Alice, which makes sense. 1 out of the total possible outcomes. A good way to check is that we got the denominator of 36, which means that we have that total number of possible outcomes on the bottom, which is what we want. Okay, number 3. What is the probability that Jared will get to take home the cookies? Meaning, what's the probability of Jared getting chosen twice? Because the person that gets chosen twice gets to take home cookies. So the probability of Jared getting chosen is 1 out of 6. And so the probability of Jared and Jared is going to be 1/6 times 1/6 again, which is 1 out of the 36 options. So those two are the same. Let's try number 4. Caleb secretly hates 3 of the people in the circle. What is the probability that he will get paired with one of them? So Caleb does not like some people in his friend group, apparently. And so we need to figure out, first of all, what the probability of Caleb getting chosen is, because he's not going to be put with somebody that he hates unless he's chosen, right? So the probability of Caleb getting chosen is 1 out of 6. And then the probability of somebody he hates getting chosen is, well, 3 of them, right? 3 out of the 6. And that just reduces to 1/2. Not that that's super important. You could have left it. We could have left it. But yeah. So now the probability of him getting chosen with somebody else. So notice that this question didn't have like what's the probability of Caleb and somebody he hates getting picked. It didn't use those exact words. Like we had to infer that the probability that we're calculating is the probability of Caleb and the probability of somebody he hates getting chosen, right? So Caleb and somebody he hates is 1/6 times 1/2, which equals 1 out of 12. That's it's pretty high chance compared to the other two that we calculated. Notice that it's not a 36 on the bottom. That's because we reduced a fraction. That's the same as 3 out of 36. So it's just a higher probability. It's 1 in 12 instead of 1 in 36. Okay, let's do this one. Jake is pulling marbles out of this bag at random. After he draws a marble, he records the result and then replaces the marble in the bag. So remember how we talked about how if you don't replace what you're pulling out of the bag or drawing out of the deck, then they become dependent. Um, these are independent because he's replacing the marble. So we're still doing the same kind of math, which is nice. He's replacing the marble, so therefore those two events are completely independent of one another. Number one, what is the size of the sample space if Jake draws 2 marbles? So first of all, if we're using this bag here, there are, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 marbles. So the first time he draws a marble, there are 10 choices. Even though he's not really making a choice, there's 10 possibilities, right? And then the second time he draws a marble out of the bag, it's also 10 choices, 10 outcomes. So the total number of outcomes is 100. Fundamental counting principle. Number 3, what is the probability that Jake will draw a white marble twice in a row? So I just colored all of mine pink, but there are 4 white marbles in this bag. So the probability of getting a white marble just once is 4 out of 10, or 2/5. I'm not going to reduce this time because I want to reduce later. And it's asking what the probability of getting a white marble twice in a row is. So we're calculating the probability of the white marble and the probability of white marble, right? Which we could write like this: white and white. And again, we just multiply those two probabilities, even though they're the same probability. We multiply them together, and it gives us 16 out of 100, which definitely reduces. That's like then 8 out of 50 and 4 out of 25. That's probably the reduced version. Yes, we are removing a marble from the bag, but we put it back. We replaced a marble. So yeah, so it's not that because we were replacing a marble. He drew out a white marble, put it back, and then drew out another white marble. If we weren't putting it back, yes, there would be a bunch of different math that we're having to do. And you would have to, as a side note, you would have to factor in somehow that they're dependent to one another. So if you pulled out a white marble, then the probability of getting a white marble would be less the second time. Yeah. So we are replacing the marble. That's why it's out of 10 both times. Okay, what's the probability Jake will draw a black marble and then a striped marble? So it just so happens that there's 3 black marbles and 3 striped marbles. So the probability of getting a black marble is 3 in 10, and the probability of getting a striped marble is also 3 in 10. So getting a black and striped would get you 9 out of 100. 100 total possible outcomes. So again, the reason that we're multiplying those two things together is because of this formula. So we're just multiplying the probability of event A, the first event, times the probability of event B, the second event. So we are just multiplying. Oops, there's an L in there. Multiply probabilities. Yes. Okay. Great, so that's not hard. You just multiply the probabilities if you're calculating and probabilities, right? Um, Now let's talk about OR. Because OR gets a little bit more complicated because it's not just one section of our Venn diagram, it's several. Remember that OR, like if you're talking about event A or event B, it includes event A happening, event B happening by itself, or both of them happening together. So those are like three different sections of our imaginary Venn diagram that we have to take into account. So it's okay, um, like to calculate probabilities when you can list out the sample space. Like we'll do in this next problem, we're gonna list out the sample space. Because then you can just count which things qualify, and then you just put that over the total possible outcomes. So it kind of works the same as the other probabilities. You just have favorable outcomes over total number of outcomes. So you can just count which outcomes are favorable and then how many in total there are. You can't always do that. So we're going to do this problem that way, and then we're going to talk about a formula that and why it works after. So in this probability experiment, we spin a spinner with A, B, C, D, E, and then record the result, and then flip a coin, and then record the result of both. So here's how I'm going to do this. The first bit is that we should list out all possible results because we can't, we need to be able to count the things that are favorable. So we need to be able to have like a whole list, a total list. So here's what I'm going to do. I'm going to start with the coin because there's only two options on the coin and I am good at that. Heads. My H is going to stand for heads. And then I could get A, B, C, D, or E for heads. So we could have heads A, heads B, heads D, I missed C, head C, and heads E. And then you might imagine where I'm going next. We're going to put tails, 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 tails A, tails B, tails C, tails D, tails E. So it looks like there's 10 total, which makes sense because with counting principle, I have five options here and two options here. So that gives me a total of 10 options when we multiply. So that's good, that checks out. So there are 10 total. So the denominator of our probability fractions should be 10 because there's 10 total possibilities. Until we reduce it, of course, because then it changes. So our first question is, what is the probability we get a consonant or heads? So a consonant, meaning B, C, or D, or heads. So, hang on. So first of all of the heads qualify because in this OR scenario, it's okay if just one of them happens. So all of the heads are good because that means that heads occurred and therefore it's a favorable outcome. Now consonants start to include B, C, and D because with the tails because we're okay if only one of them occurs, right? So, and in this section, good heavens, I can't talk yet. In this section in the middle, both are occurring. We're both getting heads and a consonant. So we have several things happening here. Notice that I just highlighted three sections from our like Venn diagram. I have one happening, the other happening, and both happening. So the thing is though, we don't want to count, we're not going to like count something twice because it's still only one event. Like both things happening does not count as like two different events. It's still the same thing. It's like one event, right, where both things happened. So we're just going to count all the ones I highlighted, which is 5 in one category and 3 in the other. So that gives us 8 out of the 10 total possibilities. I'm going to erase my highlighting because I'm worried that we're going to have to highlight something else in a second. So 8 possibilities out of 10. And we could have very easily made a Venn diagram for that. So if you like the Venn diagram idea, like go for it. I kind of like just counting which ones work, but we just have preferences. So, um, number 3, what is the probability we get B or tails? So I'm going to do a little bit more highlighting here. So any event with B is good, which are those two. Also, any event with tails is also good, which means all of these. And this one is where the double, like we get both B and tails, which is like the middle of our Venn diagram. So that gives us a total of 6 out of 10 options. Now, both of these I could have reduced. I probably should have. In fact, I don't know if MathSpace actually cares about that, but it is important. So this is actually 3 out of 5. There. Okay. Okay, number 4, how many possibilities involve getting a B on spinner? So there are only 2 events with just a B, right? You get heads B and tails B. So that's 2 out of 10. It's just asking how many possibilities, so it's not asking for a probability, it's asking for a number of possibilities, which is only 2. And 5, how many involve getting tails on a coin? So tails is 1, 2, 3, 4, 5. 5 of them. Okay, so we have 2 possibilities that involve getting a B on the spinner, and 5 possibilities that involve getting tails. So I left my highlighting because this is actually the same question as before, right? We're calculating B or tails. So number 6 asks, why doesn't the sum of your answers from 4 and 5 give you your answer from 3? So what I'm asking here is, why doesn't this plus this, 2 plus 5, equal our answer from up here? And I would encourage you to think about that for a minute. Because we had 2 possibilities for getting a B and 5 possibilities for getting a tails. Why doesn't 2 plus 5 give us the probability for getting both? Or, I mean, the probability with or for getting B or tails. You might notice that we would have counted one option too many times, right? So the possibilities with getting a B include this one and the heads B. And then the possibilities for getting a tails also like double counts this one, right? Like we counted that one twice, once in the tails, once in the tails and once with the B's. Which is why we can't just add the probabilities. Good heavens. We can't just add the probabilities because then we double count something. We count something twice, which is annoying when you can't actually just look at the list of the sample space. You can't just look at the total outcomes and just which ones work, because our calculations end up being a little bit more annoying. You can't just add them. You have to factor in the one that you counted too many times. So we'll talk about that in a second, but we would count the tails B option twice. Yeah. So here's where we come to our lovely equation. So the thing is, you will not need to use this unless you are unable to, or unwilling, I guess, if there's too many, or you can't see the sample space. If you can't see the list of all the things that are happening, then you're gonna have to use this equation. A lot of times they'll give you like a Venn diagram, like you'll see down below, or they'll give you a list of the sample space, or it's something that you can list out, like the one that we just figured out. So that option is always there. You don't need to use the formula if you can see the sample space. You can just count which ones are favorable and put them out of the total number. This is for when we don't know, we can't write out the sample space. For example, if they're just telling you how many options there are or something where you just can't really list it out. And the way that this works, the reason this works is that we first calculate the probabilities separately, just like we did in number 4 and 5 up above, and we add them. So we just add the two separate probabilities together, which again, we figured out that we can't just do that because then we end up with double counting at least one, sometimes several. So then we have to take away this part. We take away the ones that we double counted, A and B. So this is where it gets kind of funky because the probability of A and B is calculated by multiplying the probabilities of A and probability of B, right? So that's like this is the same thing that we were calculating by itself on the last page. That's an and probability, which ends up being multiplying the probabilities of A times the probability of B. But all that's doing is we're taking away just one set. So we double counted the ones that are in the middle of the Venn diagram. We double counted the ones that have both events happening. So we need to take away one set of those so that we are only left with like a flat count of everything. So we take away the ones we counted twice. So if I were perhaps to draw like a picture, oh, I also wanted to say that this is the way that you calculate that is you multiply the two probabilities together. That's the equation we had on the back page. So yeah, if that helps. So if I were to draw a picture, it's essentially like we're counting, like this is like a separated Venn diagram, right? We're counting both probabilities, probability of that happening and the probability of that happening. And then we take away the middle section where both are happening so that we don't double count them because we just counted them here and we counted them here, right? So I don't know if this makes any sense to anybody else, but this is the way my brain thinks about it. So we counted probability of this happening, probability of that happening, and take away the one set of the ones we counted twice, so that we just have a flat count of everything. So let's use a Venn diagram down here. This is one where it gives us it again gives us the sample space. So we are not needing to use this equation quite yet. We will later. But right now we can see everything, like all the results in this Venn diagram. So we don't if we double count something, it's going to be like we don't actually need to. I don't know why we would double count something. So if a student, oh, sorry, this poll is about people's activities for exercise, students' activities for exercise. If a student from this survey was chosen at random, what is the probability they choose swimming or tennis? Uh-oh. So our probability we're calculating is swimming or tennis. So first, let's figure out how many total students are in this survey because that's going to be the bottom of our denominator. So we're going to just add all of these numbers together. 19 and 3 and 2 and 4 and 9 and 10 and 4. Last time I counted, it was 51. If I'm wrong, let me know. And okay, so we're wondering whether Remember our Venn diagrams from last time. Or probabilities include this whole thing and this whole thing. Because anytime where one of those things happens or both is favorable. So we're going to count or add up all of the probabilities or all of the students that chose any of those highlighted categories. Because we're calculating that or probability. One of them is happening is good. The other happening is good. Both is great. So 19 plus 3 plus 2 plus 4 plus 9 plus 10. And that gives me 47. So there are 47 students that said either swimming or tennis was one of their activities that they did for exercise. So 47 out of 51 total students is our probability there. I also just wanted to show you what it would look like for us to use the formula for this. So the probability, we're going to calculate the probability of swimming first. Probability of somebody choosing swimming is just this inside the circle for swim here. 19 plus 3 plus 4 plus 9. Which equals 34 out of 51, I believe. No, 35. Let me double check. I'm using my old calculations, and that's always dangerous. 19 plus 3 plus 9 plus 4. Nope. Plus 3 plus 9 plus 4. Oh, it's 35. That's what was wrong. 35 out of 51. That's the probability of just swimming. And then the probability of tennis is all the people in this circle. It's not a square. So that is 10 plus 2 plus 9 plus 3, which is 24 out of 51. I randomly changed colors, sorry. And then here's where it gets interesting. So the probability of, I'm just finding all of my components first. So notice I'm doing probability of, let me get my laser pointer, probability of the first event happening, probability of the second event happening, and then I'm going to try to figure out what the probability of both happening is, which is not hard on a Venn diagram. Swimming and tennis. Swimming and tennis is, let me get a different color. How about red? Swimming and tennis is just this overlapping piece in the middle, 9 plus 3, which is 12 out of 51. So now I have all my components, right? Notice, okay, first of all, I already solved this problem. I just counted all the things that we needed together. I'm just showing you that this formula works for when you don't have a Venn diagram available for you. So if we calculate the probability of just swimming, probability of just tennis, we would add those together. So the probability of swimming or tennis is going to be the sum of the two, like all by themselves, probability of swimming and probability of tennis. So like 35 plus 24. And then we take away one set of in the middle because we double counted them. And that will give you 47 out of 51, which is what we got up above. So the formula does work. Notice that it's a lot worse than just looking at the set of sample space and counting which ones are favorable options, right? This is for when we don't have that option available, and you'll see an example of this in the next page. We'll get there. So we have another random probability experiment of rolling a 6-sided die and then a 4-sided dice. So, and we're going to change this experiment a couple of times in the questions. So first of all, how many different possibilities are there when you roll both of these dice? For the first one, fundamental counting principle, for the first one, there are 6 possibilities. For the second one, there are 4, because it's a 6-sided die and a 4-sided die, which gives us a total of 24, turn my page, total of 24 possible outcomes when you roll both of them, if you're considering both. Number 2, if we were to create a 2-digit number with the 2 dice outcomes, the 6-sided die is going to be the 10th digit. So for example, if we rolled on our 6-sided die, we rolled I'm going to zoom in. We rolled a 4 on our 6-sided die and a 2 on our 4-sided die, it would be 42. So that's what we're doing. The 6-sided die is the 10s digit, and the 4-sided die is the 1s digit. And then what it's asking here is, what is the probability that the number we get is even, which this one is, right? 42 would have been one of those situations where it's even. Now here's the deal. I don't want to list out, we could, but I don't want to list out 26 different possibilities and then just count, because there's a better way to do it. Because the 4-sided die is going to be the 1s digit, any number with a 1s digit that's even is also going to be even, right? So if you get a 4 or if you get a 2 on your 4-sided die, then your number is going to be even. The other options are 1 and 3, which are not going to it's not going to be even. There's nothing you could get on the 6-sided die could make it not even, right? It's all dependent on the 1s digit. So what we're going to do, we're just calculating what's the probability of getting a 4 or a 2 on the dice, yeah? Which we can pretty easily calculate because, so here's 2 or 4 on the 4-sided dice. There are only 4 options, right? On the 4-sided die, it's 1, 2, 3, and 4. We are focused on these 2 options out of the 4 total, right? Which means that it's half 1 out of 2. Let's start with the non-reduced. 2 out of 4, 1 out of 2. So the probability of that happening, getting an even number when you tack them together and make them one number, is half, because it's all dependent on that 4-sided die. Notice that these questions are not super specific as to what they're asking. They're not saying, what's the probability of getting a 2 or a 4 on the 4-sided die? They're asking, if we put them together, what makes it even? So notice that you have to sort of infer, you have to sort of take a couple of steps in your imagination to what the probability actually looks like when we're calculating it. So the chances are about 1 and 2, which makes sense for even and odd numbers, right? Okay, number 3. Say we take the product of the 2 dice. What is the probability that the product is an even number? So here's where it gets interesting. I want you to think about in your head for a second, what if you're multiplying 2 different numbers together, what makes the result even? I'm going to give you a second. Do some experiments in your head. Does the even and oddness of the 2 numbers that you're multiplying matter? And how does it matter? So here's the experiments that I sort of do in my head when I'm thinking of this. Like, okay, first of all, we can either have an even or an odd on the first number or an even or an odd on the second number. So let's try even Let's try even times even. Say like 2 times 4 or 6 times 2. The result is always even. Yeah? You could also have even times odd, which is like 2 times 3, gives you 6, which is an even number. I will let you figure out if you think that's always true for a second. I'm going to keep going. You could also have an odd and an odd. 3 times 1 gives you 3. So it turns out the only unfavorable option here is this odd times an odd situation. So odd times odd numbers gives you odd, but odd times even also gives you even. In any order, you could have even, odd, and then odd, even, right? So this seems like a pretty hard thing to calculate, right? Because we have 2 different dice of different numbers of outcomes. So here's what we're going to do. We're going to write this as we're going to actually go down to number 4. It says rewrite the above as a probability involving or. So with that in mind, what we're actually calculating here is the probability. Let's write it in words. How about the probability that a 6-sided dice, the shorthand for that is like a D and a 6. So don't get confused by that. That's just a 6-sided die. I don't want to write out 6-sided die. But the D6 is even, or the D4 is even. Do you see that? Because if either of them are even, then the product is going to be even. If they're both even, that's great too. The product is going to be even. The only time that they're not going to be even is if both of them are odd. So just as a side note, close your ears if you're already confused, but as a side note, the opposite of this is getting odd, odd. So you could also calculate the probability of getting 2 odd numbers and then just find out what the opposite is of that. So like take it away from out of 1, right? So like out of 12 choices, 2 of them are odd, odd. So you could take away 2 out of 12 and get like 10 out of 12 is the other option. So that's also another way you can do this. You can think of the inverse of this. But we're not going to do that because I don't want to confuse you more. I'm going to erase this because I want room. So what we're actually calculating is this or probability, even or even on the D6 or even on the D4. So first we're gonna, because we're using, first, hang on, I'm gonna scroll back to here. Because we're using this formula here, I'm gonna calculate the probability of the first die having an even, probability of the second die having an even, and then the probability of them both having an even. That's what we need to figure out so that we have all the pieces of this formula here. So the probability of, and I'm gonna call it like D6 even because it's different, I guess, for just so you can differentiate what I'm doing, even though it's the same probability actually, but it's fine. Getting an even on the D6 is three of the outcomes out of 6, right? 1, wait, not 1, 2 and 4 and 6 are all even numbers, so that's 1/2, 3 out of 6. And then the probability of the D4 being even, we actually already figured that out, is also 1/2 because 2 or 4 out of 4 different options are also even. So 2 out of 4. And I just reduced them already. Now, last step, what's the probability of the D6 being even and the D4 being even? which we know we figure out by multiplying the two probabilities together. So 1/2 times 1/2 gives you a quarter, 1/4. This is like the culmination. We're putting all of our information that we learned today together into one problem. So finally, we can put this all together into the formula here. The probability of a d6 being even or the d4 being even is we add the two separate probabilities together. So 1/2 plus 1/2 minus both of them together, which is 1/4, which ends up equaling a half plus a half is 2/2. It's 1, right? Take away a 1/4 is 3/4. So all of that work to get to 3/4 of a possibility. Yes. Hopefully that made sense. Please ask questions if you have them. I know probability is like a kind of a different kind of math. I always have to like switch my brain to do probability. It takes a lot of thinking. Number 5. What is the probability we get a 3 on one of the dice? So I'm just going to rewrite this as a or probability because I can already tell that this is an or situation. We're getting a 3 or a 3 on one dice or a 3 on the other. So I'm going to do the same thing. I'm just going to rewrite. Our goal here is to get the probability of a 3 on the d6. I don't know how to shorthand that. 3 on d6 or a 3 on the d4. So that's the probability we're calculating. I'm first going to calculate the probability of getting a 3 on the d6. It's a 1 out of 6, right? Because that's a 3, just a 3 out of the 6 possible outcomes. And then the probability of getting a 3 on the d4 is higher, right? Because there's not as many outcomes, but there's still just 1 3. So 1 out of 4 probability. And then what's the probability of getting a 3 on the d6 and a 3 on the d4? This is that part that we're taking away because we would have counted it twice. So to find that, we just multiply the 3 on the d6 and the 3 on the d4, which is 1 out of, let me write out what my math is doing, what I'm doing. 1/6 times 1/4 is 1 out of 24. Total options. So there's only one of the total outcomes that's a 3, 3 on both. So then, in conclusion, we can put that all together to get this probability, the 3 on the d6 or the 3 on the d4, equals 1/6 plus 1/4 minus 1/24. Because you add the two individual probabilities together and then take away the ones you counted twice, which is the and probability. So in order to add those fractions, we're going to have to get a common denominator. Be careful because I know fractions are a thing, and they were a thing a long time ago. So when you add fractions, you have to get a common denominator, which in this case will be 24 because actually you could do 12 too, but I don't want to do 12 because I have to take away 1/24 anyway, so I might as well just make it 24 already. So 1/6 is the same as 4 out of 24 because you multiply the top and the bottom by 4. And then 1/4 is the same as 6/24 because you multiply the top and the bottom by 6. Minus, oops, not plus, minus 1/24. So the grand conclusion here is the 4 plus 6 is 10/24 minus 1 is 9/24. So does that reduce? Doesn't 3 go into 24 8 times? So it would be 3 eighths. Is that right? Yeah. think so. Yeah, so the probability of getting a 3 on the D6 or a 3 on the D4 is 3 out of 8 possibilities. So I know this lesson gets a lot more intense than the last two. We're just sort of putting together some of the information that we had from before. So again, I will be having study sessions today. So if you would like help, please ask for it. I'm down to help you whenever you're doing your homework. So if you like, I mean, of course I do other things sometimes. I mean, not very many times, but sometimes I'm doing other things. Um, so I will be holding a study session at 11, not 11. That's only 10 minutes away. Sometime soon. Um, And if you need help at a different time of day and you're busy and you can't join me for that one, just let me know and I will be happy to help you. B days included. So if B days are better, I'm good with that too. So please let me know, and because I like to answer questions and I know this stuff is interesting. So I think that's all. Anyway, have a great Thursday, and I will hopefully see you at a study session. If not, I will see you on Monday, I guess. Bye, guys.